Marching cubes is a well-known strategy for generating smooth geometry from a density field. It's perhaps the most recognized algorithm for doing just this, and is present in so many YouTube tutorials that if we gathered all the YouTubers, we could probably run multiple IKEAs together. So why am I discussing it? Well, most of these videos are just variations in implementation of the same article to various degrees of completion. But rather than talking about that, I want to talk about how to properly use marching cubes, as in addressing the various challenges and benefits that comes from using it in a large-scale game. I touched on these concerns extremely briefly in my previous video, avoiding going into depth on it as the video was admittedly more entertaining than serious at times. But I thought for those interested, I'd start a new longer form series where I discuss how to address these concerns, more as a code guide than a showcase, so we won't have any of these segments. So as a recap, in case you didn't watch the other 100 videos on this, marching cubes is an algorithm that converts a density map into a mesh, which is how our pipelines draw something to your screen. It does this by considering each cube independently and generating geometry for it based on the density of its 8 corners before combining it all to form a mesh. There's obviously a bit more to it, but in general that's all it is. There, you're welcome. I just saved you 8 hours of your life. As I said, it is slightly more complicated than just that, but I will only get into those parts as they come up. So for now, this is basically all it does. Right off the bat, you might notice there's a clear difference between marching cubes and traditional voxels. If you look at this diagram of 4 adjacent chunks and watch as I color code them into which chunks each voxel belongs to, we can see, well, everything is nice and organized as we expect. But let's try to do the same thing with marching cubes. Remember, unlike cubic voxels, marching cubes generates geometry between each sample rather than right around it. We find that on the border between chunks, we have samples that somehow belong to 2 chunks at once. This is not a mistake. In fact, for any size chunk, you will find that its border will always be shared with its neighbor. Now believe me, this is a very annoying problem, and is a large reason why many people give up on using marching cubes, so our first order of business will be addressing this. When developing an actual game and not just a terrain generation demo, there's several guidelines that exist that should generally not be broken. Number 1. Chunk generation should be as functionally independent as possible. Number 2. Voxel data should have a fast and readily available access and modify pattern. Number 3. There should be a ground truth to all data. Chunks should be as independent as possible, not only because it allows easier parallelization, but also because it gets rid of what I'll refer to as the border chunk problem. For example, suppose each chunk relies on 4 bordering chunks to fully generate. If we support generating chunks in a 4x4 radius, then because these perimeter chunks don't have their neighbors, they'll generate incorrectly, requiring us to regenerate them when their neighbors are actually visible, or maybe more simply, not generate them at all. 2. Voxel data should have a fast and readily available access and modify pattern. When developing an actual game, you'll find that many systems require knowledge of a voxel's information. Depending on your game, you may find these queries can happen quite a lot and quickly become the bottleneck of your application. For these reasons, it is generally not preferred to use types of references which may require many branching checks for different possibilities on where its actual data could be. 3. There should be a ground truth to all data. This should go without saying, but if the game itself cannot agree on a single source of truth, how can we expect the player to? With computers, it is common for data to be duplicated in the name of efficiency, but a reliable application should always be able to discern where and how it can achieve the ground truth for all data it needs. Keeping these guidelines in mind, there are 2 main approaches developers often take when encountering this problem. 1. We can allow chunks to maintain their own copies of these vertices. 2. We can allow chunks to look into their neighboring chunks. Between these 2 options, most developers at first choose the prior, the primary reason for this being that it is ultimately easier to program. Though it may not seem this way at a glance, as synchronizing 2 independent copies of data without communication seems difficult, and to an extent this is true later on. When terrain generation is entirely noise-based, this matter is as easy as sampling the same position twice. Unfortunately, this strategy violates the second guideline we discussed, and to a lesser extent, the last one as well, and for those reasons, it's not used in Artera. Synchronizing this data may seem easy if it's only generated one time, but in our game, where a mountain of systems can modify the terrain, it quickly becomes unmanageable if every modification has to synchronize across multiple copies, sometimes up to 8, some of which may not even be loaded into memory. If any of these copies encounter a race condition and desync, then we violate our last guideline of a ground truth, which can cause obscure bugs where no system can agree on what a voxel is anymore. However, it is worthwhile to note that this is only really a relevant issue if the terrain map is mutable, as in if it can be modified in-game by the player or natural events. In many games where the terrain is just the background, these concerns are a non-issue, as any copy we read will be the same, so duplicate vertices is by far a simpler option. If that's you, congrats! Instead, if your game features terrain interactions, using the second strategy is almost always a better option. With it, each voxel owned by a chunk is uniquely owned, and we never have to synchronize any of its data across chunks. On the other hand, the second strategy violates our first guideline, meaning we'll have to devise some synchronization to allow chunks to safely access their neighbors, and a solution to the border chunk problem. A very intuitive way for chunks to find their neighbors is to place them in a 2D or 3D adjacency array, where each chunk is stored based on its spatial location, meaning a chunk's physical neighbors are also its neighbors in this grid. It really doesn't get any simpler than this. But this implies that we have a finite amount of chunks, which is obviously not the case in our infinite world. Luckily, if we are smart and assume the amount of chunks we can render at one point is finite, we can use this cheeky formula to place new chunks in a way such that they replace old chunks no longer in view, while still maintaining the adjacency property. Well, what about the border chunk problem? Well, we could just not generate these perimeter chunks and delay it until all their neighbors are present, but that seems kind of wasteful. If we look at this graph of how many chunks we are wasting, the raw amount of chunks grows astoundingly quickly, even though the percentage of chunks we are wasting actually decreases? Listen, okay, I did it this way, so I'm just going to explain it. Instead, we'll get around this with a hybrid approach, whereby if chunks detect they are on the perimeter, they'll sample their missing duplicate data, which technically belongs to their neighbors. Then, when their neighbor actually arrives, the chunk will regenerate using its actual neighbor's information. Actually, having an answer to this question helps us resolve another question developers often encounter when they want to create smooth normals. Under marching cubes, each mesh vertex generates on an edge with 2 endpoints. Usually to solve for normals, we look at these points to see how the density is changing around them, and then blend between the two directions by where the vertex is on the line. But in certain situations, we could be solving for a vertex whose parent could be in a different chunk, which in turn samples further into that adjacent chunk, or maybe another chunk entirely. So having an answer to how to do this with either more duplicates or a lookup strategy is essential if you want your chunk borders to look nice. Now, let's figure out how to render this geometry. If you look at many of these terrain generation demos, most of them render geometry by coloring triangles based on how high they are in the world, or maybe off some on-demand noise maps, or most commonly, based on the gradient of the terrain. But we want to assign colors based on the actual voxel information, so this requires us to save the material information in each vertex during generation, so we can use it to look up a texture when rendering. And that's really all there is to it. I don't know why I made a section for this. There are a few points to be aware of, such as when pushing vertex information into the pixel shader, make sure you use this noInterp flag so it doesn't try to flash through the entire texture table between edges. Mainly, I wanted to bring this up because this guy on Reddit was confused on why I mentioned I didn't use surface nets in my other video. In short, with mushing cubes, each vertex is situated on an edge with exactly one underground parent, meaning it's very clear which material a vertex should adopt. But with surface nets, it's not as clear. Without going into them too in depth, each vertex under surface nets is situated entirely within a voxel where multiple corners could be underground, hence it's just a bit more ambiguous and complicated to find a clear material assignment. Surface nets do have several advantages though, in that they can create sharper shapes and most times generate less geometry, so if you're interested, there's also a mountain of videos on it as well. Understanding that, let's now talk about how to remove duplicate vertices generated by marching cubes, which is a large bottleneck in rendering speed. To recap the issue, yes, recap because I definitely brought it up earlier and didn't just shrug it off. Because each voxel is processed independently, if everyone generates all vertices used by its triangles, we end up with a lot of duplicate vertices. Now the actual solution this guy was talking about is related to realizing that we can construct a full grid of squares by just combining 2 edges of every pixel. Basically, if we enforce that each pixel only generates vertices on its bottom 2 edges, we can store these vertices in a lookup table, and then follow up with a second pass allowing triangles to reuse these vertices across pixels. Now bringing it up to 3 dimensions, we can reduce our 12 edges down to 3, meaning we can estimate our gains to be about 300%, and indeed, this seems to be about correct. Also, if you're interested in implementing this, be aware of voxels on your top faces, as you'll have to process them to populate vertices on their bottom 2 edges, even though these vertices aren't technically owned or even in the chunk. Now that we've discussed all the simple stuff, we can finally move on to the real challenge of using marching cubes. If you thought what we discussed before was difficult, all these problems are turned up to an 11 when creating levels of detail. Problems looking for a neighbor's voxel data? Try doing it when the neighbor isn't even the same size. Problems finding which chunks to replace? Try having to replace multiple chunks at a time. Problems regenerating chunks? Try doing it while having to keep track of when chunks are fully covered. Having trouble knowing when to regenerate a chunk? Try having to also account for regeneration based on when a chunk's neighbor changes size. Also, we have these large cracks in our terrain that we cannot just fix with marching cubes. This is where the thinking cap comes on, and I have to actually apply my computer science degree that I haven't even earned yet. First, I'll be addressing the complications brought on by octree levels of detail specifically, before discussing more general detail level problems in Transvoxel. So if you're not interested, skip to this timestamp. The simplest way I can think of to allow our lookup tables to support chunks of different sizes is to allow chunks to write multiple entries in our array. If we suppose our lookup tables just store the address to the chunk in memory, when other chunks look up this information, they end up wasting a lot of time trying to figure out where the specific quadrant they are interested in is in the larger chunk. So, we'll add this little info blurb that's unique to each entry overlapped by the chunk, and we'll tell the requesting chunk the offset of the region they just queried. Now, other chunks just need to follow these steps to find out their neighbor's information. Another unique problem with octree-based detail levels specifically is that we'll often be trying to regenerate the same region of space with a different sized chunk. But because this is done asynchronously, as it should be in any large-scale generation, if a chunk is replaced by smaller chunks, most times these chunks will not arrive at the same time. If we immediately delete the larger chunk once any part of it has been replaced, then for several frames, we get a visual gap in our world which can be very jarring. Likewise, if we never delete the larger chunk, we'll obviously run out of memory at some point. So, to get around this, we'll be creating a new concept called zombie chunks. Basically, when a large chunk is being replaced by smaller chunks, it'll become a zombie and stay around until it is fully covered. To tell if it is fully covered, when a chunk finishes rendering, it'll call this reap function which traverses the octree upward, checking whether any parent or larger chunk is fully covered and releasing them if they are. This applies to our adjacency lookup table too, and we'll have to keep track of how much each chunk is dereferenced so we can safely release its data only when it is likewise fully replaced. Now, it's time to fix these large gaps created between detail level borders. These exist because when we have two detail levels bordering each other, the higher level of detail can introduce these intermediate samples which may create dips or holes that are invisible to the lower level of detail. So to resolve this, we'll be using this Transvoxel algorithm which surprisingly doesn't have that many popular videos explaining. Basically, it takes the idea from marching cubes where 8 points can only have 2 to the power of 8 states and extends that to a border voxel with 9 corners. With why 9? I can clearly count 13 corners here. Well, with transvoxels, these 4 corners in the back are the same duplicated 4 corners up here that we've just pulled back a little. With this understanding, Transvoxel is basically the same algorithm as marching cubes, with the same unreadably large lookup table, paired with just a few other concerns, such as shrinking the corners and so on. This is where most of these academic videos will stop, so if you were planning on watching them, I guess I saved you another 30 minutes. However, this Transvoxel paper only supports a detail level jump of 2, but what if we want to scale really quickly, maybe with a detail jump of 4 or 8? Well, to do this, there's a really obvious solution that surprisingly isn't brought up often, layering 2 transition voxels on top of each other. In fact, we can layer as many of these transition voxels on top of one another to bridge any power of 2 decrease in detail. The way I've coded my implementation to do this is to have the CPU configure the layers based on the calculated detail difference on each of its borders, and then have the GPU use a bunch of magic matrices to map each face correctly. While this may not be the most readable solution, it's not like I coded the rest of this to be readable either. Lastly, we need to remember that if a chunk's neighbor changes its detail level, then our transition voxels will now be connecting the wrong level of detail. So keep in mind to recheck a chunk's neighbor periodically and refresh the chunk if its neighbor moves levels. So now, with all these considerations, we are finally able to create the fluid open world experience using marching cubes you can find when playing Arterra. All in all, there's quite a bit of consideration beyond these marching cube tutorials in bringing these experiments to a fully polished game experience, and I'm sure there's a ton of concerns you might face personally if you decide to tackle these problems yourself. So for help, I've also attached samples to my marching cubes, Transvoxel scripts, and my blog that goes deeper into these topics in the description for reference, in case anyone is crazy enough to program it all in a computator like me. I originally intended this video to be more of a narrated coding format, but I guess I just couldn't help myself. So if you like this form of content, or would rather prefer a talk and code session, please let me know by liking and commenting below. But until then, stay tuned.